So should we start? So today I wanted to continue talking about quantum dynamics a little bit. So let me recall what we said last time, and let's focus on pure states. So we've got, as usual, the finite dimensional Hilbert space H. So we have a special observable H, the Hamiltonian. And a pure state is defined by a vector of unit lengths. So then we have this Schrödinger evolution. Oops. So that's the linear first order differential equation which determines for us the evolution of this vector. Let me recall, or let me tell you one simple fact. Under the Schrödinger evolution, the length of the vector which defines the state does not change. So that's a very simple fact, but let's still prove it. Well, for that we simply compute this derivative. Well, it gives us two terms. And in each of the terms we can use the Schrödinger equation. So now let's recall we decided the Hermitian product is linear under the first for the second vector and antilinear for the first one. So this means that we'll get I over H, and here the sign changes because of the complex conjugation. And here we'll have HU U minus U HU. Right? So now this difference is zero because H is an observable and an observable is self-adjoint. Right? So this is zero because H star is equal to H. So that's the proof. So basically there are two things. We added this I in a good place. And also H, the operator that we're using to generate the evolution, is a self-adjoint operator. So for this reason, the length of those vectors does not change. That's actually looks like a very small thing, but in many physics stories it plays an enormous role. So we'll return from time to time to this notion that H is self-adjoint, and you do need, typically in quantum theory, you do need this self-adjointness for many things, and it has just Okay, that's one simple computation, but on the physics side, it has lots of interesting manifestations. Sometimes people also say that, right, this length of the vector, if you look at it on the probability side, that's like a total probability that your system, say you have a system and there are many possible outcomes, what can happen to it, but the sum of probabilities of outcomes must be equal to 1. So that's the origin of this 1 here. So, and from this perspective, this equation is telling you that the probability, the total probability, does not decrease and does not increase, which is somehow good, right? Because the sum of all outcomes should be always 100%. You cannot, like with time, go to the situation when the sum of probabilities is only 50%, because then what happens with the other 50%? So that's the meaning of this equation. Now, one more remark about the quantum evolution. So let's denote the eigenvalues of H. So that will be the set, let's say E1, Ek. So recall that we denote them E, and it stands for energy. And let's say the corresponding eigenspaces are, or let me even call them H1 to Hk. Recall that if we have any vector u in H, it can now be uniquely decomposed into the sum of vectors in H1, Hk. And now, if we act by the Hamiltonian, by the operator H on Ui, it will simply act as multiplication by the eigenvalue Ei. Well, now in terms of this decomposition, we can easily solve the Schrödinger equation. So recall that the Schrödinger equation now says that du over dt is minus I over h hu. Now let's just substitute this decomposition. On the one hand, here it will be du1 over dt plus duk over dt. And on the other hand, we can simply act on the sum. So this will be minus I over h E1, U1, minus so on, minus I over h Ek, Uk. Right, so here we have a sum of vectors in those orthogonal subspaces, H1 through Hk, right? And here we have also a sum of vectors in those orthogonal subspaces. So actually this equality means that for each I, we have dui over dt is equal minus I over h ei ui. Now this is a very, very simple ordinary differential equation that we can solve, right? So the unique solution is ui of t equal to exponential minus I over h ei times t times ui of 0, right? So that's a solution of this differential equation. Let's keep the setup for a moment and let's write it down. So now we have u of t is equal to the sum from 1 to k. Here we have those exponentials So this is this quantum evolution equation, and this is its general solution. So you can vary those initial data, right? Of course, you can start with different pure states in the beginning, and that's everything that happens. So you have those complex exponentials which turn with time, and depending on the initial data, that's what happens. As I say, maybe sorry for repeating it, right? That's how the quantum evolution of the universe looks like, right? Isn't it like kind of stunning? Can it really be true, right? That's it. Well, universe or not universe, let's look at some simple example of quantum evolution. So let's take H equal to C2 as usual. Now I would like to choose the following Hamiltonian. Let's say it will be just a 2 by 2 diagonal matrix with eigenvalues alpha and minus alpha. And well, this would allow hundreds of physics interpretations, but one possible physics interpretation is like this. We consider an electron in the magnetic field. So let's say, so here is the z-axis, and there is a magnetic field along that z-axis. And we have an electron. We already know that the electron is a spin 1/2 particle, which means it's described by this Hilbert space C2. And well, it turns out that the Hamiltonian in the general case is some kind of constant and multiplied by this combination of Pauli matrices which represent observables in the Hilbert space of the electron and the components of the magnetic field. And now if the magnetic field is along the z-axis, so these two things, they are not present, and so the Hamiltonian is some constant mu times bz, whatever it is, times this sigma matrix sigma z, which is 1 minus 1, and so actually in my notation here alpha is mu times bz. So you can even visualize it in some physics terms if you want, but of course mathematically for us, well, it's a well-defined and very easy problem. So let's see what's the solution of this problem. So now so the eigenvalues of H in this case are alpha and minus alpha. And eigenspaces, so they simply spanned by the first and second basis vectors in C2. Now, what will be the solution of our problem? So let's say u of 0 is equal to, let me see what I want to denote them. Yeah, maybe it's somewhat ugly, but well, u1 of 0 and u2 of 0. So let's say that's my initial state. So then we should be able simply to write down, right, the answer for the state at the time t. So here we're just using this formula, right? So for the first component, the eigenvalue is alpha. For the second component, the eigenvalue is minus alpha. So this means that here we have exponential u1 of 0, and here exponential of I over h alpha t u2 of 0. Right, so that's a general evolution. Now let's look at the particular example. Let's choose u of 0, for instance, equal to this expression, right? 1 over square root of 2, 1 over square root of 2. So this is a vector of norm 1. So that's a possible initial state. So then, of course, we'll have u of t equal to 1 over square root of 2. And here there will be these two exponentials, right? Well, now let's try to solve some kind of quasi-physical, let's answer some quasi-physical question. So now we have an evolution of some quantum state. We started at 0 from this thing. Now it evolves, and that's what we get at any given time t. Suppose now that we want to measure something. Well, we know that here we have those observables. We know all the observables for this Hilbert space. Let's choose the observable, say, sigma x. Right? Let me recall that this is simply this matrix. So this is one of the possible observables. Now, this observable will have a mean value at any given time t. Right? So let me recall that this mean value, this will be the trace times the projector, or maybe a simpler formula for us. It will be given by this expression, right? You should act by the vector, by sigma, by the operator sigma x, and take a Hermitian product again with the same vector. So if we again try to imagine it physically, so we have this z-axis, and we have somewhere here an x-axis. So we started from some original state. We are running our quantum evolution. To run quantum evolution, you just need to wait, right? Time passes, and the quantum evolution develops. And then you want to measure at some point the x projection of this angular momentum. And we know that all those sigmas, they all have eigenvalues plus or minus 1. So basically, you will see that it's either this way or that way, right? So there will be two possible outcomes, but with some probabilities. So that's what we are computing now will be the the mean value of this sigma x depending on time? Well, let's compute it, right? So what is it? Sigma x bar of t is equal to what? So this will be 1/2, and here will be the product of this guy u of t, so exponential minus I over h alpha t, exponential I over h alpha t, and here I need to act by sigma x on that guy, and this simply, because sigma x is this matrix, it simply interchanges the components, right? So this will be h alpha t alpha t. So this will be Hermitian product of these two vectors. So let's recall our Hermitian product. It applies the complex conjugation on the first component, right? Oops. So I think, if I'm not mistaken, the outcome will be 1/2, and here exponential of 2I over h alpha t plus exponential minus 2I over h alpha t. And this is what? This is cosine alpha t 2 alpha t over h. So that's if I'm not mistaken. Now, how is it? There are some qualified physicists in the audience. So what does it mean, this result? What would you say? What is your physics interpretation? Okay, so that's the outcome, right? The mean value is this cosine. So what actually happens?
Like some kind of precession from...
Sure. It is like one should imagine, okay, one should imagine something like this. So you have a magnetic field along the z-axis. You put there this poor electron which rotates. It has a rotation moment, and as a result it has a magnetic moment, and the magnetic field starts turning it around the z-axis, right? So there is a rotation around the z-axis, the precession, as you say, and that's why the x projection, it periodically changes with time. Now, however, notice that it's an interesting way how it changes. So the eigenvalues of sigma x are equal to plus and minus 1. So that's similar to sigma 3, to any other sigma. So actually, the quantum theory tells us that if you measure sigma x, you will always get either plus 1 or minus 1. However, the probabilities with which you get them, those change. And sometimes the cosine is equal to 1. This means that actually you will certainly find plus 1. Or sometimes the cosine is equal to minus 1, and then you will certainly find minus 1. Or on some occasions, the cosine is equal to 0. And this means that you will, with equal probability, find, you just don't know. You measure, you find either plus 1 or minus 1 with equal probability. So that's a very simple example, but it's a typical example of what we are interested in, or what we might be interested in quantum theory, right? So quantum mechanics, that's the dynamical system which produces you outcomes like this. So you have, you choose an observable, you choose a Hamiltonian, you choose the initial state, and this produces for you a family of problems. So all those problems you can basically solve in that way. Right. So we'll return to it many times, to this context, but let's keep it in mind, right? Here, it's all very much under our control. It won't be always the case, that I can tell you. But But that's in a nutshell what quantum mechanics is, right? So that's this theory. Now I want to talk a little bit more about the structure of what's going on. And typically, when we have some framework, we can ask about symmetries of that framework. So I would like to talk a little bit about symmetries of, in quantum mechanics. So we'll be speaking about symmetries at two levels. So let me first introduce the so-called Lie algebra of symmetries. So let me fix a Hamiltonian H of a quantum system, and let me define the following space. So recall that last time we had introduced, in addition to observables, the imaginary unit times observables. So they form a Lie algebra. So I consider the following elements of this Lie algebra, which have a vanishing bracket or which have a vanishing commutator with the Hamiltonian. So in fact, Sim H is a Lie algebra. So what does one need to check in order to prove it? So in fact, we already have elements of the Lie algebra IA. So under the commutator, IA is a Lie algebra. So the only question is, suppose we take a commutator of two such guys. Will they again satisfy this equation, right? So suppose I take a commutator of B1 and B2 and consider the commutator with H. Now, let me write a formula and you tell me whether it's obvious. Probably for some of you it's immediately obvious. For the others, I don't know. So here is the instance of the Jacobi identity. Right, the Jacobi identity you can write in many different ways, but that's one of the forms of the Jacobi identity. Now, since this equality holds true, you see if the commutators of B1 and H and of B2 of H are equal to 0, then the commutator of the commutator with H is also equal to 0. So equal to 0 if B1, B2 are in the symmetry Lie algebra. Now, just one remark about definitions. Suppose B is a symmetry. Then I can multiply it by I or by minus I, as you wish. So now this is an element in A, right? This is now an observable. So if you take a symmetry, you multiply it by whatever, any pure imaginary number, you get an observable. And this observable, of course, commutes with the Hamiltonian, right? because B commutes with a Hamiltonian, so A commutes with a Hamiltonian. So this means that A is a conserved quantity or integral of motion or quantum integral, how we said it last time. Of course, the other way around. Suppose that A is an observable and is a conserved quantity. So then you can take B just by multiplying by I or minus I, whatever you want. And this will be an element of symmetries of H. So in the first class, I asked who of you knows classical mechanics, and some of you know classical mechanics, and some of you don't know classical mechanics. But just for those who know classical mechanics, maybe recall that in classical mechanics there is this big thing which is called the Noether's theorem. So who heard of Noether's theorem before? All right, so yeah, half a class. So for those of you who know Noether's theorem, you probably recall that in classical mechanics it's a big deal, right? It's an important and relatively complicated statement, right? Which exactly relates symmetries and conserved quantities. Well, you can say this is a kind of quantum version of the Noether's theorem. The only thing is, right, it is completely trivial. It's like, it tells you that if you multiply, if you had something which commutes with H, you multiply it by I, it still commutes with H. So maybe, so this is a quantum Noether's theorem. Well, probably here it does not quite deserve the name theorem because, right? Or you can also formulate it as a slogan. Conserved quantities generate symmetries. So it goes both ways, as we see. Given a symmetry, you automatically get a conserved quantity. Given a conserved quantity, you automatically get a symmetry. Perhaps now I would like to go to another level and introduce the following notion. So let me take a capital letter S and say that sim H is the following. So this will be now unitary operators which satisfy this equation. So the conjugation of H by G is equal to H. So let's discuss this notion. So this is the now symmetry group of H. First, I guess, hopefully, right, everybody knows the notion of a group, right? And is it obvious that this is indeed a group? So why is it a group? Okay, let me check one thing and you tell me why the other things work. Suppose that You have two elements and they're both symmetries. So then the product is also a symmetry. And that's simply because of the following. If you conjugate by G1, G2, this means conjugating by G2 and then conjugating by G1. But each of those conjugations, it produces for you H, right? So the conjugation of H by G2 is H, and then the conjugation of H by G1 is still H, right? So similar for the inverse. Now, actually, we know how those symmetry groups look like. So let me recall that H can be written as the following. Let's write H in the basis of eigenvectors. So how does it look like? So there is a block with eigenvalue E1. Then there is a block with eigenvalue E2, and so on. And a block with eigenvalue Ek. So those blocks may be of various dimensions. For instance, they can all be of dimension 1 in principle, or H can have just one eigenvalue. So everything is possible. Now, so what is your expert opinion in linear algebra? How would this symmetry group look like? Right. So we want to have all the unitary operators. Now, since we are working in a concrete basis, all unitary matrices, which conjugates in this guy give the same guy. So what are they?
Like basis for the eigenspaces.
Sorry?
Each, like in the first n columns, you put a basis for the first eigenspace.
So you mean here right? So here would be some matrices, right? Conjugation with those matrices preserves H. Now, so you're suggesting to put something concrete. You say some basis.
Yes.
But which basis?
I mean, like an orthonormal basis corresponding to that, like each block of columns corresponds to a basis for the eigenspace corresponding to the eigenvalue.
I think what you're saying is correct. Can someone reformulate it in somewhat more manageable terms? So how do they look like, those matrices here? Right, of course, they are block diagonal with the same blocks. I think that goes along the way of what you were suggesting. Now, what is in the blocks?
Unitary matrix.
That's right. So here would be, let's say, let me call them G1, G2, GK. So GI is in U of HI. So basically here you have independent blocks. So those blocks, they don't talk to each other, right? So each block acts on the corresponding eigenspace. Those eigenspaces are called HI. And you just ask them to be unitary. That's it. So maybe Let me give a couple of examples. The first example let me take H to be in the diagonal form. It has two eigenvalues which are the same and one eigenvalue which is different, right? So then sim H, this will be a unitary group of this H1 times the unitary group of H2. And the standard notation for unitary groups of the space of some dimension, this is U of the dimension. So let me call it U2 times U1. So that's the notation that people typically use. And more concretely, this means that here you have a block diagonal shapes. Let me call it AB minus B bar, A bar, Z, right? For those of you who kind of worked with it before, right? That's the form of an arbitrary element of a unitary group in the two-dimensional space. So absolute value of A squared plus B squared is 1, and absolute value of Z is 1, right? So this is U2, and this is U1. So that's one example. And the second example would be like this. So let's say our Hamiltonian now has all the eigenvalues different, right? So now this symmetry group is U1 cross U1 cross U1, or one can put it this way. So these are diagonal matrices, and absolute value of all the eigenvalues is equal to 1. So that's the symmetry of this Hamiltonian. Now, let me finish this hour with one more slogan. But first, maybe your judgment. What do you think? Which symmetry group is bigger, this one or that one? So what's a bigger group? In fact, here this question has a direct meaning because one of them is a subgroup of the other one.
First is bigger.
The first one is bigger, right? Here you can, oh, maybe here I actually, oh, what I said was actually wrong, right? Yeah, sorry. What's the correct thing to write there? It was too restrictive, what I wrote. Okay. Yes. Yeah. Yeah, it didn't match because I wrote wrong conditions. Yeah, but in any event, this one is bigger because in particular you can put those Z1, Z2. This will be a 2 by 2 unitary matrix. So, and the slogan is as follows. More symmetry means more degeneracy. You see here there are two eigenvalues which are the same, and there is an eigenspace which is of dimension 2. Or one says that this eigenvalue is degenerate, or it has a multiplicity. And the manifestation of it is a bigger symmetry. And in the other way around, we know that if we have a bigger symmetry, right, if we have those unitary groups bigger, it needs to have multiplicity of the eigenvalues. So we'll return more to this discussion from time to time, but basically once you see a multiplicity of eigenvalues in the quantum system, you're supposed to see some symmetry which corresponds to it. All right, so let's have a break and let's continue the discussion of symmetry after the break. All right, let's continue. So I would like to add some simple remarks about symmetries. First of all, let's rewrite this equation for which is a definition of symmetry. In the following way. So this implies that GH is equal to HG. And this has very nice consequences. Suppose that U is an eigenvector of H. Then GU is also an eigenvector. Well, that's because if you act by H on GU, you simply use this identity, you interchange them, and this simply gives you the same eigenvalue. So that's maybe one observation. So the other observation, suppose B is in the symmetry Lie algebra of H. Then its exponential is in the symmetry group. So why is that? There are probably many ways to see it, but maybe one way to see it is as follows. So let's recall that the exponential is defined by this formula. And the definition of symmetry is that B and H commute. So H commutes through everything. So this is an absolutely convergent series. I commute H through each term of that series, and I simply see that this element commutes. And I think that we already seen once, but also we know that this is a unitary element. That's because you can put star under the exponential. B star is minus B. And by the property of the exponential for matrices or for operators, this is the same as exponential B minus 1. So this means that this element G is unitary and G commutes with H. So which shows that it's actually a symmetry. One more remark. Which is a somewhat obvious remark. If we multiply h by I, of course we obtain an element of symmetries of h, right? H commutes with itself, so it generates a symmetry. And this also implies that the evolution operator, which is an exponential of some particular b, right? It's also an element of the symmetry group. In fact, here maybe people with physics background can share their knowledge, right? So right, we say it's a symmetry. So the Hamiltonian generates a symmetry. The evolution operator is a symmetry. Now, what is this symmetry? Right? After all, so we have a system, and it's supposed to be in some way intuitive, right? It's supposed to be some kind of physics. Physics means that we are supposed to have some feeling about it. Now, we have a symmetry, and this is a God-given symmetry for any system, right? Any system comes, at least this is certainly a symmetry. Now, what is this symmetry? So what does the physics wisdom say?
Time translation.
Yeah, so this is, and well, time, yes, that's right. So this is the time translation symmetry. Of course, the fact that this is an evolution operator, it already hints about time translations, right? What does this thing do? It takes the state at the time 0 and it brings us to the time t, right? And it turns out to be a symmetry. In particular, if you started with an eigenstate of a Hamiltonian at the time 0, we know that the time evolution will continue to be in the same state up to the phase rotation, which is in some way even not completely physical. Actually, the state given by an operator would simply not change, given by a projection would simply not change. So also maybe here, we'll come back to it later in the course, but just think about it. What happens if the operator h is time dependent, right? From the very beginning in the axiom about the Hamiltonian, I said that the Hamiltonian is a fixed observable. But of course, as it usually happens in physics-related stuff, axioms is a somewhat flexible matter. I can actually change my axiom and say that, well, it's a self-adjoint operator, which may possibly depend on t. Right? Then, of course, the Schrödinger equation becomes a more complicated equation, and yeah, then you may ask what are the notions of the symmetry? Would the evolution be still a symmetry? So this becomes more complicated. But in our simple-minded framework, the Hamiltonian generates a symmetry, and the evolution operator is a symmetry of the system. Now I would like to discuss another question also related to symmetries. So up to now we were saying that we fix one observable, the Hamiltonian, and we look at the symmetries of that Hamiltonian. Now let me do the following. Let me add to the Hamiltonian some number of other observables. Let's say A1, AM. So then, in principle, nobody forbids me to ask for a symmetry for the whole system. So the definition is obvious. I'm simply asking for the Hamiltonian and for all observables to be conjugated to themselves. So that's a perfectly valid definition. It's easy to check that this is again a group, a subgroup of the unitary group. Now those subgroups may become somewhat more complicated, but well, so what? And related to this definition, there is another very interesting, again, very simple but very interesting definition. Which is as follows. So we say that a Hamiltonian and some set of observables is a quantum integrable system if the following conditions hold true. First of all those AIs, they are conserved quantities. Second, they all commute among themselves. And the third, that the symmetry group of this system is minimal possible. What's the minimal possible symmetry group in this situation? So I want it to be the product of U1s n times, where n is the dimension of H. So let me say this definition in a slightly different manner and then give examples. So you see, so we have a number of observables, a number of self-adjoint operators which all commute with each other. Remember that the main thing about self-adjoint operators is the spectral theorem, right? Now what can we say about the spectral theorem for those operators? So we can find a common basis of eigenvalues, right? So then we can actually re-say this statement in the following way. Joint eigenspaces of H, A1, AM are all of dimension 1. So all the joint eigenspaces, they are one dimension. So let me show you a couple of examples. In fact, maybe even 3 examples. Actually, we already seen them today. So let's say H is diagonal, and it has eigenvalues 1, 2, 3. Well, I claim this is a completely integrable system, right? So you don't need to add anything, actually. You can, but you don't need to, right? This guy has a simple spectrum. All its eigenspaces are already of dimension 1. Now the other Hamiltonian that we had today was of this form. 1, 1, 2. Now it does have a degenerate spectrum. So here the eigenvalue 1 has multiplicity 2. So this wouldn't do. So we need to add something. For instance, what about adding this guy? Is it an integrable system? So recall, we need the joint eigenspaces to be of dimension 1, right? So now the joint eigenspaces are all of dimension 1. What happens if I put here, say, 1? Is it still an integrable system? Yes. Note that this guy has degenerate spectrum. So this guy also has a degenerate spectrum. But the joint spectrum is non-degenerate. Because, for instance, for 1, 1, you need to take an intersection of this eigenspace spanned by E1, E2, and this eigenspace spanned by E1, E3. And this is only E1, which remains. Is it clear what I'm saying? Or? Okay. You can also like forget this A, and I suggest another A. Is this thing an integrable system? What's your judgment? Okay, yeah, that's clear, right? It's quantum mechanics. There are 2 answers, yes and no, right? they probably have some probabilities, right? Right? How they can come up. We need to verify various conditions. The first condition, whether H and A prime commute. Do they? Yes, they do, right? Because the unit matrix commutes with everybody. This is block diagonal. This is block diagonal. All right, so this guy commutes with that guy, so they commute. Now, whether the spectrum is simple for both, for the pair. What's the spectrum of this guy? What are the eigenvalues? 1 minus 1, exactly. So they're different ones. So on this subspace where this guy is degenerate, this guy has eigen values 1 and minus 1. So therefore the degeneracy, how people say the degeneracy is lifted. So these are all integrable systems. So HA and HA prime are integrable. Now, maybe let me make a contact with some other field, of math. So let's assume that H, A1, AM is an integrable system. So then, there is a basis of H which consists of common eigenvectors, right? So let's what does it mean? So this means that on each of those vectors all our observables on the list, they simply act by multiplication by some number, right? Now let's consider the following set. Right? So these are the set of vectors, we can say, right? So those vectors, they have real components because they are eigenvalues of observables. So this is a subset of R to the power m plus 1, some finite subset of R to the power m plus 1. And so here let's consider our basis from 1 to n. So this is a subset of H, right? So these are vectors in H. So there are exactly n elements in the basis, and there are exactly n elements in this set. And of course, right, he explicitly enumerate the vectors E by those A's, which go from 1 to n, and we explicitly enumerate the elements of this set by the A's, which go from 1 to n. It is obvious that there is a one-to-one correspondence, a bijection between these two sets. What's the field of math which studies bijections? How is it called? So it's called combinatorics, right? So this is a very, very trivial observation, so to say, which actually used a lot in interplay between quantum theory and combinatorics. So of course, all bijections, they're in some way obvious when you've made them obvious. Before you made them obvious, they are not necessarily very easy. So that's the way to generate bijections between subsets of a vector space, like basis of a vector space, and some kind of sets of numbers or vectors of numbers. So those numbers typically on the physics side They're called quantum numbers. So this is now what we see is a bijection between a basis in our Hilbert space and the set of quantum numbers. Like, for instance, in this example, we have a basis of our three-dimensional Hilbert space, which consists of the three standard vectors, E1, E2, and E3. And we have those joint eigenvalues, which are 1, 1, 1, minus 1, and 2, 1. So these are, so to say, quantum numbers. And the bijection defined by the quantum integrable system is this map. So a quantum integrable system defines for you a bijection between a basis in the Hilbert space and the set of vectors. Now, maybe one more remark. About integrable systems. So suppose we have a quantum integrable system. What we can do, we can introduce some kind of modified or multi-time evolution operators. So let me write them down. So I simply add more parameters, and I ask those observables which make on the list of my integrable system to correspond to the shifts of those parameters. Of course, this means that instead of just one Schrödinger equation, we add m equations which correspond to the evolution with the time ti. It's easy to see that this is still unitary. And this is still a symmetry. Now, on the mass side, this is often used, such evolutions with many times. On the physics side, it's not entirely clear what would it mean. You can think about the following philosophical question. Of course, if your Hamiltonian already has a non-degenerate spectrum, so then you don't need to add anything to make a completely integrable system, right? Now, maybe the fact that in our ordinary life we observed only one time and not many times, maybe that's just a manifestation of the fact that the Hamiltonian of the universe is non-degenerate. Who knows, right? Maybe otherwise we would have observed those other times or not. So, but that's on the philosophy side. Okay. Very well. Now I would like to formulate one of the big problems in quantum mechanics and in mathematical quantum mechanics. Right? We've seen that once we know the spectrum, to a large extent, the quantum problem is solved. Of course, there are still things to do, but basically we need to know the spectrum of H, and if the spectrum is degenerate, we would like to find a completely integrable system. So that's a setup of one of the basic problems in quantum mechanics. Obviously, as all basic problems in mathematical physics, it doesn't have a recipe for a solution. So there are solutions in some cases. And I would like to spend the next lecture on showing you one non-trivial example of solving such a problem. But today we still have a quarter of an hour, and I would like to introduce that problem. In fact, it resembles a lot the problems that you already saw in the exercises. And it goes under the name of the Heisenberg magnetic chain. So as usual in a quantum problem, you need to first choose the Hilbert space. And the Hilbert space will be, again, finite dimensional. You already saw this relatively involved construction of a tensor product. But now this will be huge. A huge tensor product of many copies of C2, and potentially this n can be very large. Up to now in the exercises we saw the examples when n was equal to 2. Now we take n of arbitrary size. Now there is a nice piece of notation that I would like to introduce, the so-called SPB notation for the operators acting on this space. So recall that already in the exercises you saw that you can, for instance, introduce operators by acting only on one copy and acting by one on all the other copies, right? So these were some of the examples you saw in the exercises. Now on one copy, we basically know all the operators acting. These are Pauli matrices. So for this reason, it's convenient to introduce a special notation for an operator which acts by one in all the copies, and it acts by sigma A on some copy somewhere in the middle, maybe a copy with number I, and then it continues to act by 1. So, and in general, we'll be using the superscript I, for something which only acts on one of the copies, on the copy I, and on the other copies it acts by 1. In particular, now what happens, right, with this notation? Suppose that I is different from j, and you want to multiply two such operators. Well, then it's obvious that you can interchange them, right? Because one touches only one of the copies, the other one touches only the other copy. Those copies, they don't talk to each other. So it doesn't matter in which order to apply those operators. So we'll work more with this machinery. We'll develop more of this notation next time. But now let me talk about the Hamiltonian of the system, its interpretation, and start discussing its symmetries. So, so let me write it in the following way. So this will be sum over I from 1 to n, sum over A from 1 to 3, and here sigma AI, sigma A I plus 1. So these are operators acting on this huge space, right? First of all, remember, as in one of the problems, we take a sum from 1 to 3, which means sigma x, sigma y, sigma z. So, and we apply them on the neighboring sites. Now, there is one small thing that you should have asked me, but maybe you had no time to look at what I wrote. So here the sum is from 1 to n. What does it mean if I is equal to n? Oh, maybe, sorry, capital N, right? Because the n plus 1 does not exist. So, so here I just use the notation that n plus 1 is equal to 1. So actually, this means that the guy number n here is paired to the guy number 1. Now, what's the physical idea of it? So you have a chain, and on that chain you have your spins, whatever, electrons or whatever you want. And so this is basically the scalar product of those two spins. So you have two spins, and the contribution into the energy or into the Hamiltonian is the scalar product of these two spins. Now I left some room here, and let me write here some constant, J. And if this constant J is bigger than 0, right? So then what will happen, or maybe let me start with the example of J smaller than 0. So if J is smaller than 0 and those spins, they look in the same direction, so then you get a negative contribution in the energy. And typically on the physics side, lower the energy, more favorable is the state. So that's the intuition. So this means if J is smaller than 0, then you would think something like this will happen. Probably those spins will all align. And that's what is called a ferromagnet. So that's a model, or a very simple-minded model of how magnets work. But then if J is bigger than 0, then they don't want to be aligned. They want to be aligned in the opposite direction. So you can imagine something of this sort intuitively. And this is called antiferromagnet. But frankly speaking, we don't care so much, right? So that's just to give you an intuition where this model came from. What we are interested in is the following. All right, now we have a concrete Hilbert space, and on that concrete Hilbert space we have a concrete operator. This operator is constructed in a somewhat strange way, but well, this is clearly a self-adjoint operator, and one can ask how to compute its spectrum, what are the degeneracies, how to build the corresponding integrable system if needed, and next time I will show you the answers to those questions. So I should say, maybe just a small warning. Up to now, I think in some way, I don't know how difficult you find the course, but up to now it was a kind of relatively relaxed walk through linear algebra, right? So next time, at least for those of you who never seen it, like this will be one class which will be of a different kind. So it's a complicated and interesting machinery. It will be kind of more difficult, more interesting as well. So, and then we'll go back to school for some other topic. But next time will be an interesting class. Maybe the last thing before we end, again, building on the exercises. So we're interested in the symmetries of this Hamiltonian. We're interested in the degeneracies. And one small remark is as follows. This is also similar to exercises we had before. Let's introduce operators which take a sum of all sigmas with a given index for all possible i's. So this is something like this, sigma a times 1 plus 1 sigma a 1 plus so on. And I think in the problem set you saw that in the problem set you saw that for n equal to 2, so these are actually conserved quantities, right, for that Hamiltonian. In fact, I think it is now obvious that this is true for every n. So why is that? That's because you need to establish the fact that the Hamiltonian commutes with LAs. Now, the Hamiltonian consists of many terms, but every term, it uses only 2 neighboring sites, right? Now, LA consists of many terms, but each term is only using 1 site. Now, what will happen when you commute H with LA? Let's choose, for instance, this term. Now, all the sigmas, with the exception of those with indices I and I plus 1, they are kind of irrelevant, right? Because here you will have ones. Ones commute with everything. So the only terms which will be relevant in LA, these are the terms with sigma I and sigma I plus 1. So this becomes a computation for 2 sites. But the computation for two sides, that's the computation that we are doing in the problem set. So actually the computation of the problem set tells us that each term in the Hamiltonian actually commutes with each L. But if each term in the Hamiltonian commutes, the whole Hamiltonian commutes as well, right? So this is actually equal to 0. Right. So in fact, historically, as far as I understand, what happened is the following. So this was obvious for the people. So there was this model, and it was obvious that this is, so this is a symmetry. So these are conserved quantities. So this symmetry would imply that you have some degeneracy of the states. Now the question is, like, what's the, is it enough to explain all the degeneracy? And it turns out that this is absolutely not the case. So this explains to you why there is part of the degeneracy, but the degeneracy for H is absolutely huge. So this means it has hidden symmetries, symmetries that you don't see. So those symmetries, well, are easy to guess, but the question is, what are the other symmetries? Or in other words, what are the other operators which commute with this guy? Well, frankly, like kind of, I don't know, it's not obvious for you, I guess. It's certainly also not obvious for me, okay? There is this sum of products of those matrices. It acts in some way on this huge Hilbert space. What are the things which commute with it? All right, so next time we're going to discover how to see them. Okay, that's it for today.